let's welcome the first speaker of the day, first speaker of the week, first speaker of the program, Professor Eknath Ghate from Tata Institute of Fundamental Research, and he will be speaking on Introduction to Modular Forms, Elliptic Curves and Modular Curves. And let's go for the ride.
Okay, so thank you very much to the organizers for organizing this slightly unusual topic for the Indian number theory community. Just a few people doing it here. Maybe that comment applies to almost everything in India. There's just a few people doing anything. So anyway, it's forced me to look up various references from many years ago, 15, 20 years ago, and rethink some things. It's a fascinating topic. I mean, how can you not like a topic where the primes dividing the order of the monster group are the same as the X naught P genus 0 curves, right? This should just itself, or maybe X naught plus P, that should itself tell you this is like a very fascinating thing. And if you think that that's very old-fashioned, well, the papers that I don't understand very well, but now these infinite modular curves, which are perfectoid spaces. So you have the whole gamut. You can choose where you want to enter into this area. So I maybe am at the more classical end, but yeah, there are fancy techniques now that are being applied to modular curves of infinite level, p-power level. There was not much communication, perhaps maybe a good thing between the various speakers. So my brief, I understand, is to give some very basic background on some of the definitions. So that's what I'm planning to do. I've organized my lectures around the following theme, that the space of modular forms has an integral structure. So I think this is one of the requests from one of the other speakers. But that will appear maybe in the third or fourth lecture. So I'm actually going to give a proof using the Q expansion principle. But there are at least 4 proofs of this. Maybe there are others. There's also a proof using Jacobians, which is in Diamond-Sherman's book, reference 1. There's a very old proof due to Shimura, Shimura isomorphism, which I might just write in one line somewhere, maybe in the second lecture. And of course, there's a classical proof. You know, as I said, this subject you can do at any level. You can just try and write down an explicit basis of modular forms over Z, right? So for example, if you have level 1, then multiples of E4, E6, and delta, there's that 4A plus 6B plus 12C, everything. Everybody knows what I'm talking about, right? Equals the weight. That forms a basis. And so you can try and do classical things like that. So yeah, there are many different ways to approach it. And maybe the way that I will do it at the end is maybe the fanciest. It uses the most algebraic geometry. But there are proofs which don't use any algebraic geometry. For example, the Eichler-Shimura isomorphism. So that's the theme of my lectures. But I'm going to give many elementary definitions. So for the experts here, you're going to be a bit bored. My apologies in advance. Okay, so let us start. So today I thought I'll just mention the modularity theorem. This was another request from one of the other speakers, and maybe say a little bit about the moduli interpretation of the modular curves. Okay, so modular forms. Lectures are not designed for my, the boards are not designed for my height. Be at least a foot taller, I think. But okay, I will go on my knees if I need to. Modular forms. So H, I'll just write the usual Roman H for the upper half plane, half complex plane. And SL2Z. It's all matrices with integer entries. And determinant equal to 1. It's a group. This acts on the upper half plane via, he knows this. Okay, I think I need to write tau to follow Diamond-Sherman. I might switch to Z's or Z's, depending on which country you're living in at some point. So make sure I go back to taus. So I'm basically following Diamond-Sherman for the first 3 lectures because diamond im, which is what I was asked to lecture on, is a bit terse at the beginning. I mean, there are lots of formulas and things. Diamond Sherman is spread out over 6 chapters, whereas those sections in diamond im are very short, maybe 4 or 5 sections. So you can look at diamond Sherman, but broadly following diamond im if you want a condensed version. Okay, that's the first 2 references. They're also on the web page. And these are lurking in the background. These are 3 Japanese guys. Can you guess who they are? Shimura in the 70s, very famous book. Miyake, the 80s. He in the 90s. He also has an elementary, he has 5, 6 books, but the first one he ever wrote, the word processing is not very good, but it has many things on modular form. So for example, the Shimura isomorphism is very well done here. It's not in here. And Miyake has many elementary classical things which are nice too. Also the trace formula and things. Anyway, so those are, but these are, I think these 3 books are a little more scary, a bit more advanced, and this is sort of perhaps at an appropriate level. Okay, so, yes. So this acts on the upper half plane because of the formula that the imaginary part of tau z, or sorry, imaginary part of gamma tau, let's call this gamma, is some formula, which is part of tau, the determinant, Cz plus d, plus d squared, which is positive. My taus are not looking very much like taus, so yeah, so if tau is, the imaginary part of tau is positive, then imaginary part of gamma tau is also positive. Okay, so what is a modular form? It's a holomorphic function. So weight k greater than or equal to 0, 1, take 1 here is the holomorphic function. In the upper half plane to the complex numbers such that the values at those 2 points are almost the same, but not quite. They differ by an automorphy factor, which depends on this parameter k. So c plus the values are differ by c tau plus d tau times f of tau. So all gamma belonging to SL2Z, tau belonging to the upper half plane, knows that. And also f is holomorphic at infinity. So the upper half plane, it maps into the unit disk. So because this identity here, this function is periodic. If you take gamma to be the silly matrix 1, 1, 0, 1, then this is just z tau plus 1. This is just tau plus 1. So f of tau plus 1 is equal to 1 to the power of k times f of tau. So it's periodic with period 1, and therefore you can make the following change of variables. Get q to be e to 2 pi I tau. And think of it as a function on the punctured unit disk, the complex plane instead. And as such, it extends, that's a removable singularity, and it extends to a holomorphic function there. Okay, so one very nice property of the modular forms is they have Fourier expansions, and this is the reason that number theorists are interested in them, because these Fourier coefficients often turn out to be integers and encode many, many different things in number theory. So thus, it's holomorphic. These guys have Fourier expansions, Taylor expansions, whatever you want to think of, where the ANs a priori are complex numbers. As I said, one of the points of these lectures is I had to sort of have some theme, is to show that these numbers are actually algebraic under some good conditions. just some integers or algebraic integers. Your coefficients. So let's make the following definition, notation. MKSL2Z is going to be all the module forms of weight K for SL2Z. You can add two things, even multiply two things, but the weight changes, adds, forms a ring. And you can also multiply by scalars. So this is just a vector space if you fix the weight K. So I won't have time to do examples, just a survey, whirlwind survey of things. But you really have to, if you haven't seen modular forms before, and I'm sure everybody here has, but if you haven't, maybe one or two you haven't, then you really have to sort of sit down and work out some nice examples. And the basic example is Eisenstein series. It'll take me too much time to get into that now. So I'm not going to describe Eisenstein series, but they're in all books and you can just look them up. Okay, so sometimes more interestingly, once one wants to speak of plus forms, so let's define those also, and modular forms of higher level, etc. So that is also define those. Definition. Form of weight K n equal to 1 is a plus form where the boundary is. It's over there. That's not a space. If A naught in the Q expansion is 0, and this Q expansion over here, A naught is 0. I.e. F, and people just say this informally as saying F vanishes at infinity. Technically, it's Q equals 0. So again, some notation, we let SK SL2Z be the space of plus forms, subspace of plus forms of weight K. Okay, so I think that's all I want to say about these spaces for now. Maybe the most interesting example here is the delta function. And everybody, I'm sure, has seen this, and if you haven't, then just look it up. You can spend a whole 1 hour talking about just the delta function. I've done that before. In fact, that talk that was referred to in the outreach was about that topic. Okay, so higher levels. So again, my apologies for introducing all these very basic things, but I guess somebody has to do it. Usually left to the old fogies like me. Okay, so set gamma n to be all matrices in SL2Z such that A, B, C, D is congruent to 1, 0, 0, 1 mod n. I'm not going to write the word mod. I'll write round brackets. I hope it's clear. So for example, gamma 2 means that A is congruent to 1 mod 2, A and D are odd, and B and C are even. And then we have some other very important so-called congruent subgroups. The same thing. Here it's congruent to 1 star 0, 1 mod n. And finally, gamma naught n all matrices which are congruent to star star 0 star mod n. So this is the preimage of the Borel subgroup in SL2Z mod n. And the middle guy is the preimage of the upper unipolar matrices. So a subgroup of SL2Z mod n, the preimage of that in SL2Z. Okay, so definition. Holomorphic function is a modular form of weight k greater than or equal to 1 and level n greater than if so that equation over there expanded a bit, a tau plus b instead of gamma tau equal to cz plus d to the k of tau for all ABCD belonging to the appropriate group. So, I mean, I think the most general thing to look at, sufficiently general thing to look at is gamma 1n. So, gamma 1n, yes, and tau belongs to the upper half plane as usual. So, F satisfies this infinite system of functional equations. And also F is holomorphic at the, so there's a cuspal condition. Holomorphic at the cusps. Not yet vanishing because we're still speaking of modular forms. So let's see if I can do that in this much space over here, i.e. So there's no real notion of vanishing at a cusp. You just move everything to infinity and then speak of holomorphicity at infinity. So for all S belonging to, this is a projective line. You can think of that as A colon B, where A and B are rational numbers, both non-zero. Equivalence classes of such pairs up to multiplication by non-zero constants. So for all, this is a set of cusps. All S cusps with S is equal to alpha. Maybe I should write gamma here. Alpha is going to be a complex number. Let me stick to gamma for matrices. Gamma times infinity. This is diverging a bit from Diamond-Sherman. So this is a rational number, right? I just said it's A colon C, but you can also think of it as A over C. As long as C is not zero. If C is zero, then you think of it as infinity. So there's a matrix gamma. E and C are co-prime, they're in lowest terms, so you can find a B and D in SL2Z such that this holds. And well, SL2Z acts transitively on the cusp. Not so hard to check. And so the condition is, and I have run out of space. So F is Y for all S with this, comma, the condition is that F slash alpha of tau, which is defined to be F of gamma tau times C Z C tau plus D to the minus K, this function, with strange, you put the CZ plus D to the thing on the other side, so minus K. So this function is holomorphic at infinity in that sense. Okay, so for each S, you require this condition. Not the original function, but this is an action which will come up again and again. I'll define it a bit more generally in other lectures. For now, this is okay. So this is a definition. This function should be holomorphic at infinity. This looks like infinitely many conditions, but it's in fact finitely many conditions. Let me just make sure the audience is with me, especially the younger students. Why is this only finitely many conditions? I'm not writing the answer. I'm going on with my lecture. Somebody can tell me the answer. Drop silence. Why? So for cusp forms, you're required to vanish at infinity. Because, you know, gamma n, for instance, or any one of those subgroups is a finite index, right? And this condition is not saying much when, I mean, f slash, you change this gamma by something in gamma 1n, then this function is invariant, right? So you don't get any, only have to check it on those cosines. Okay, so some notation, let me write it here only. So we have the following picture. Mk gamma 1n and M, okay. The bigger the group, the fewer the modular forms because there are more conditions to be satisfied, right? So Mk gamma 1n contains Mk gamma naught n. Of course, the cusp forms are sitting in here. Okay. I think that's enough for modular forms for now. Any questions so far? Okay, great. So let us move on. The next thing I want to do is define elliptic curves and take a little bit of time. And when I'm done with that, I want to state the modularity theorem. I'll use some words when I state the modularity theorem, which have not so far been defined, not have been defined till that point, but hopefully by the by, all the definitions will be made. It's better to see it right at the beginning. Okay, so easily spend a month or two talking about elliptic curves, maybe even a semester. I have 15 minutes to do this, maybe half an hour. So I'm going to try and give a whirlwind overview of elliptic curves, and there's two approaches to this. There's the complex analytic approach, where elliptic curves are tori, complex tori, just C modulo lattices, right? Like C modulo the Gaussian integers or something like that. And then there's the sort of more, this is the topology approach maybe. And then there's the more algebraic geometry approach where you think of solutions of cubic equations, right? And these two theories coincide with cubics. So, okay, let me say a few words about each of these. Okay, so next section is elliptic curves. Okay, so definition, we'll start with the topology approach to elliptic curves maybe, and then make it match with the algebraic geometry approach. So a lattice, I'm trying to make these lectures sort of accessible to a master's student, so even below a PhD level. So trying to define everything as much as possible. Maybe by the fourth lecture, I won't be able to do that, but for now I'm trying to do that. So a lattice in C is, well, let me just say, is a lambda subgroup of C of the form Z omega 1 plus Z omega 2, where omega 1 of omega 2 are linearly independent over R vectors. a discrete subgroup of C. And it's convenient to normalize this choice of, you can always replace omega-1 by minus omega-1 to make this condition true, that the imaginary part of omega-1 over omega-2 is positive. See, this part is already we're trying to connect this already in some way to the first section, the section on modular forms. Okay, so small lemma. When are two such lattices the same? I always assume this condition that the imaginary part of whatever basis vectors I'm taking is positive. This order omega-1 over omega-2. When does this happen? Well, these are just subgroups of C. We're just changing the basis, right? So there just should be a matrix in GL2Z or GL2Z, which takes one to the other. Right? But you want this, because of this condition that the imaginary part of omega-1 over omega-2 is greater than 0, if the imaginary part, your matrix better lie in SL2Z. Otherwise, it'll take something from the upper half plane to the lower half plane. Okay, so this is almost self-evident, but check it carefully if you don't believe it. There exists some ABCD in SL2Z, which takes one basis to the other basis. Okay. Definition, complex torus. Is C modulo lambda. So this is an abelian group. And of course, because C is an abelian group, additive group, lambda is a subgroup, it's a quotient group. It's also, as we learned in our topology classes, usual picture of some parallelogram and you're gluing the opposite sides. It's a compact Riemann surface of G-1. It's an abelian group. It's a compact Riemann surface. Dimension 1. -1, one whole. Okay, so here is an important fact that one needs. I'm going to try and do one proof in every lecture, but maybe not this one. So every non-zero holomorphic group homomorphism, C mod lambda, suppose you have two complex tori, C mod lambda prime, is of the form multiplication by alpha, basically. Alpha is a complex number, non-zero. Square bracket is equivalence clause, I mean, in the quotient group. Some non-zero complex number. With some property. The reason that I'm sort of doing the complex things, you may wonder, because there's a workshop on rational points and modular curves, is that in the modular interpretation, first it's good to think of them as the complex. First, it's good to think of the complex points, and then later try and generalize one's intuition to points defined over arbitrary basis. Okay, so I think it's healthy to do the complex case first, otherwise maybe it looks very abstract. Okay, so with the property that alpha of lambda is sitting in lambda prime. So I said homomorphism. I didn't say isomorphism. an isomorphism, then alpha of lambda has to actually equal to lambda prime. How would you prove something like this? Well, okay, so you can look at Diamond-Sherman, but so Shimura, for example, finds this too easy to even bother giving a proof. So there are things like that in Shimura that one has to deal with. But Diamond-Sherman is a bit more sort of complete for a beginner. So what would one do? So we have this map C mod lambda to C mod lambda prime, right? And you have these universal covers. So the first thing is to lift this map to a map from C to C, which you can do because both the fundamental groups here are trivial. Push forward of here and all the way here are trivial, right? And lift maps. There's some inclusion relation between the fundamental forwards of the fundamental groups. Everything's trivial there. So you can lift the map. So if you have your phi tilde here, I'm just giving a sketch. I said I wouldn't prove it. Phi is your map. You have some lift phi tilde. You study this map phi tilde. And you try and show that phi tilde that the derivative is 0 at every point. Sorry, a derivative is a constant. Try and show that the derivative is a constant. Okay, so that's what one has to do. Yeah. I don't know how worth it is to go through all the details right now, but yeah, it eventually winds up, you do have to use Liouville's theorem at some point. So you'll have some entire function which will be bounded, and that winds up being constant. And then when you differentiate some equation there, this constant goes away and you get derivative 0. Sorry, the derivative is 0 maybe. Okay, so I don't want to guess the proof now, but something elementary. All right, so I'll use this without warning. It looks a bit, it's sort of magical. And here you have an abstract holomorphic map, and it's given by something very simple, just by multiplication by alpha. So this is very surprising when you first see it, and I think it's worth working out. You should do that at your own time, maybe. Okay, so for example, let's use this immediately. To divide our lattice by omega 2 to make our elliptic curve, our abstract complex torus, isomorphic to one of a more special kind, where the second basis element is 1. Okay, so I'm not giving the details of this proof. Okay, so now, using this fact, you can, as I was saying, multiply by omega 2 inverse, and this will, so there's an analog of this fact when you put isomorphism everywhere. So I just said homomorphism. If you have an isomorphism, this becomes an equality. So multiplying by omega 2 inverse takes this lattice, which was z omega 1 plus z omega 2, to the following slightly more simple lattice, lambda tau, which is z tau plus z, where tau is omega 1 over omega 2. Right, so we're beginning to write these lattices with one basis vector to be trivial. The other basis vector isn't actually in the upper half plane. The various normalizations, which you had fixed at the beginning. Okay, now tau is clearly not unique. Right, because you could have started with another omega 1, omega 2, differing by some SL2z, right? And that would have been the same lambda, but clearly tau prime equals A tau plus B over C tau plus D also works. CD belonging to SL2Z is also possible. Right, so you don't get a unique tau out of this. If you had chosen your basis in some other way, you would get another tau. Right, so you want to get a unique complex number out of this, you can't do that. You get a sort of a something in the upper half plane modulo SL2Z. Okay, so get a map from complex tori, isomorphism classes, to isomorphism to points in the upper half plane modulo SL2Z. Right, starting from any complex tori, we just associated a tau, and tau wasn't unique. And it turns out that we actually get a bijection here. Okay, so there's some small things to check there maybe, but this is true. So I'll use this again and again. So this is just, right, this was isomorphic to this abstract complex torus was isomorphic to a particular one. You can always assume you're of this kind and you map it to that tau. That was not well defined, it's only well defined up to SL2Z. Right, so let's move to the, so that's maybe what I wanted to say about complex tori for now. Let's move to the algebraic geometry interpretation of elliptic curves. So for this, there are these classical, maybe 18th century functions. Weierstrass P function. So you can begin to see why tau was used on the upper half plane, because there's also these complex parameters on the complex plane, and then these are z's, z's everywhere, and taus were for the strictly for the upper half plane. So it's a nice convention in many books, in Sherman also. Okay, so this is the famous Weierstrass P function. It will take some lectures to study its properties of this and of its derivative, but let me just summarize some things here. It turns out that the field of meromorphic functions on your torus, C mod lambda, definition, field of meromorphic functions, doubly periodic functions, if you want to think of them as functions on C, is basically generated by two functions, the Weierstrass P function and its derivative. Okay, so this is what I meant by this could take several lectures. So anyway, so this is what it is. But the point is that these maps, rho and rho prime, they satisfy the following cubic equation: y squared equals 4x cubed minus g2 lambda x minus g3 lambda. Maybe I'll write it as a map rho of z, rho prime of z, rho prime is a map from z to rho of z, rho prime of z, and they satisfy this cubic equation. Z maps to. Okay, so we have, it turns out that this is true. So this is all part of the theory of elliptic curves over the complex numbers, but from the algebraic geometry point of view, maybe. Okay, and what are these numbers G2 lambda and G3 lambda? There's some constants depending on your lattice. So this one is 60, summation 1 over omega to the 4, and G3 lambda. Notice the 2 becomes a 4 and the 3 becomes a 6 conventions. 140, summation 1 over omega 6. The prime means you sum over everything. I didn't say it maybe earlier. You exclude 0. All these sums are, you exclude 0 because I want to divide by 0 here. The main things to check that the series converge, etc. Okay, and these are also, of course, related to Eisenstein series, which I skipped, but fine. All right, so what about the group law? So C mod lambda is an abelian group. What's the group law on the other side? It's the following. Well, you graph this cubic. This picture again is in many places. You take 2 points on the cubic P and Q, and take the vertical line passing through the third point. There are 3 points generically. This line meets this curve in 3 points because it's a cubic curve. Take the vertical line passing through that point. This is, you define this to be P plus Q. This defines a group law on the set of solutions of this cubic equation. And under this isomorphism, the group law on the obvious group law on C modulo the lambda coincides with this very beautiful picture, group law given by that picture. Right, write down formulas, the group law becomes much more complicated. Yes, yeah. So you have to take a point at infinity, that's true. So as Chandrakant is saying, one should take the projective curve here, and the origin will be something like 0, 1, 0. The point at infinity was actually connecting this point, and this point. Just to connect it to a beautiful discovery of Manjul Bhargav from his student days. He found, so there's a 10 of, I'm on the camera, I think, but I think this is roughly right. I haven't prepared this, but there was in Gauss's disquisitionism arithmetic K, if I said that right, there's some 10-page formula on being able to add quadratic forms. And he used a very similar picture to make that into sort of just one picture. So this complicated group law of adding various coordinates is just given by that one picture. So if you have a matrix with integer entries at every point, you can form a quadratic form in various ways. So you can, if you slice the matrix through the middle, you'll get a matrix here and a matrix here. Let's say integer entries. So let's say capital M and capital M. So you multiply capital M by little x and capital N by little y, and you look at the determinant of mx minus ny. You get entries like 3x minus 4y, 2x minus 7y. In that big matrix, you take the determinant, you get a quadratic form, right? You slice it another way, you get another quadratic form. You slice it the third way, you get another quadratic form, and the sum of those 3 quadratic forms is 0. That's based on this thing. So based on the big same principle for elliptic curves. All right, so I think I can finally state the modularity theorem for elliptic curves. We have maybe all the ingredients. I'm going to need some words like new form, etc., but it's fine. Come to those later. Okay, so modularity theorem. This came out when I was a graduate student in 93, in my second or third years, caused a revolution earthquake in the world of mathematics. And it turned out not to be right. And then I was still a graduate student in 94, got corrected, etc. So a lot of excitement at that time. Especially so because the introduction, if you read it very carefully, Wiles acknowledges Hida quite a bit there. Maybe BBC and Simon Singh didn't do that in their book, but if you read the introduction, his work is used in many different ways, at least in 2 ways, maybe 3 ways. Anyway, so what's the theorem? The theorem is that suppose you have an elliptic curve which is now defined over Q. So those numbers, G2 and G3, they were just some complex numbers, but you could think of more generally cubic equations defined over the rational numbers. So I think you always have a model, you can forget the 4. Let's look at this language where you have some smooth cubic, there's some discriminant not equal to 0, etc. I'm not writing it down. So you have some elliptic curve given by this cubic equation. So there's some numbers you can attach to it. One is the conductor of the elliptic curve. Okay, so every time you have an equation over Q, let's say over Z even, you can reduce this mod P. And even though it's smooth over Q, it may not be smooth over Z mod P. Maybe some singularities. That happens for finitely many primes. Essentially, the conductor is a product of those primes. Some exponents there that also intervene. So let me not try and define that. It's a bit complicated anyway. But as soon as you have an elliptic curve, you have a conductor. And another thing you get as soon as you have an elliptic curve is a bunch of numbers indexed by the primes P. So in fact, even indexed by the natural numbers. So how are these defined? Well, you define them for the primes first. So if you avoid the conductor, I just said that this elliptic curve, this tilde means you reduce the coefficients A and B, think of them as integers, and you go mod P, you get an equation over a finite field. You can count the number of solutions. Generically, it'll be P plus 1. But BP is the error. So for P not dividing N. Okay, and for P dividing N, you can define BP some ad hoc way. 0 if P squared doesn't exactly divides N, or P squared divides N, and some other cases. Okay, let me try not to go into them all of them. So this gives you B at prime numbers. So you can extend, let me not give too much theory here. You can extend this to all natural numbers by basically on something like on 2 primes BPQ, you just define it to be BP times BQ. Right? P and Q are primes, co-prime, etc. So there are ways to extend these formulas to get these numbers Bn. So just starting from an elliptic curve, you immediately get a sequence of integers, sequence of errors, so to speak, the errors to the exact number of solutions. The difference between the exact number of solutions and P plus 1, basically. Okay, so we get these numbers. And so the modularity theorem of Wiles says there exists, given such a, for all elliptic curves, E should have maybe been on this side. So there exists a modular form. I hope I defined this notation. I think I did. Yes, I did. So there's a modular form of weight 2 and level n. I should also probably say isogeny class, etc. So I'll come to that in a second. So there's a modular form of weight 2 and level n, where n is this conductor. That's the level. There's a modular form of that weight, which is nice. So nice here means it's a normalized. These words will come up in the lectures as we go further. Normalized new eigenform, new form. Let's include eigenform and new form. New form. It's a cusp form of level n and weight 2. Such that, so as soon as you have an Fn, you get Q expansion. So you get An, and the Ans turn out to be in Z. In Z, they turn out to be integers. As we were saying right at the beginning, modular forms are interesting for number theorists because modular forms with good properties, the Fourier coefficients are actually integers. And this is an example of where these integers actually are counting something. They're counting these points mod p. So the modularity, this is the sort of naivest way maybe I can think of explaining the modularity theorem. So there's a modular form with all these properties, with the Ans and Z, and the final punchline is that with An equal to Bn for all n. So this is, as I was saying, you can fine tune this a little bit. This is essentially a bijection as well. If you work up to isogeny here over Q, but let's not get into that now. Maybe a bit later. So isogeny classes of elliptic curves, conductor n, are in bijection with these modular forms of weight 2 and level n with integer Fourier coefficients, new forms, eigenforms normalized so that A1 is 1. This normalized means A1 is 1. A0 anyway is 0. The cusp form. Okay, Wiles as in Wiles, Taylor-Wiles, and Roy, Conrad, Diamond, Taylor. And there's another way to say this in terms of some analytic number theory objects. So if you don't like this looks too elementary to you and you love like Dirichlet series, well, on both sides, in the world of complex analysis and in the world of geometry, you can attach zeta functions or L functions to the object you're studying, and it says that the L function attached to F is the same as the L function attached to E. The L function is just this Dirichlet series. The definition is S n equals 1 to infinity. S is a complex parameter. The part of S is sufficiently large to make this converge. We have these two infinite series mimicking the Riemann zeta function. And another way to say that is that the two L functions coincide. Of course, this implies that, but it's not so clear maybe that that implies this. So the various versions of the modularity conjecture, each time we study something, following Diamond-Ames' article, one can restate the modularity theorem in that particular language. There'll be 3 or 4 times that the modularity theorem will come up. I'll try and say it in various settings. Okay, great. So brings me to the last topic, which is the moduli interpretation of modular curves. So it unifies this lecture. Of course, the modularity theorem unifies things, but yes. Yes. Sorry, what is difficult? I don't think you need, you can actually define if you look at Silverman's undergraduate textbook, he literally writes the group law down, given in X1, Y1 and in X2, Y2, you can define the group law. It's not very enlightening, yes, because it's just formulas, but what proof of? Associative law, okay, yes. I don't know this 9 point. It's a geometric lemma of some kind on the Vesu's theorem. Okay, yeah. I don't know. I haven't thought about this for a long time, but I mean, of course, mechanically one can just check it. But using that picture, I'm sure it's fairly obvious, right? Yeah. So if you have an obvious proof using the picture, then why do you want another proof? Okay, maybe. Okay, yeah. Yes. Sure. Yeah, so that's true, of course. Yeah, I was transferring the group law from this side to that side. So of course it's a group law, so it's already associative. I think he wanted some various variants of the proof. I'm pretty sure that if you play with this picture, it'll be pretty clear that the group law will be associative, right? If you do P plus Q plus R in two different ways, you'll have to draw 2 or 3 pictures maybe and get the associativity. You can try it. We can try it at lunchtime. Yeah. Whether there are other proofs. Maybe you're thinking of some proof using the Jacobian of the elliptic curve, which is itself. Is that what I'm hearing from one of you? Someone said divisors. So that's what. Yeah. So we'll come to Jacobians. At that point, maybe you can tell me if you see some new proof. All right. So where was I? Yes. So the last section. Maybe let me erase the whole. Okay. Yeah. Erase this also. How that's proved is another story. Very interesting story, but a little bit maybe old now. So maybe I won't get into it. Read about it. Okay, so now we're moving a little bit towards the rational points on modular curves, but I'm still going to work over the complex numbers today and actually in the next 2 or 3 lectures even. And at the end, maybe over more general basis. When you first see this is a little bit confusing because these words appear again and again in different contexts, and you have to sort of isolate things. The modular curves are also moduli spaces of elliptic curves. Modular forms are functions on the upper half plane. Modular curves are basically upper half plane modulo SL2Z or gamma 1n or something like that. Right? So you have these curves. I'll define them in a second. On the one hand, you have modular forms which live on the numerator of modular curves, but the points of the modular curves are parametrizing elliptic curves with some level structure. And all elliptic curves are also modular, that theorem, right? Same actors, but different place. Okay, so for gamma equals gamma naught n, let's try and do all of these at the same time and maybe just prove one. So I'm going to look at open modular curves. So open one makes sense because there's no closed yet. But so for gamma, one of these 3 groups that we've introduced already, let's look at the orbit space H mod gamma. And let's call it Y of gamma. So we have maps. Projections. So this is an open Riemann surface, just a Riemann surface. In future lectures, we'll compactify it, etc. And that's a little tricky, especially if you want to give a modular interpretation of the compactification. a little tricky. One needs to introduce something called generalized. So generalized elliptic curves, or more precisely, Néron n-gons. So I don't know how much of that I'll do. I prepared it, but let's see. It'll show up maybe in the last lecture. So for now, let us stick to the open modular curves. The definition. So there's this word called enhanced, which is, I think, particular to Simon Sherman. An enhanced elliptic curve for gamma naught n is a three-part definition. Is a pair consisting of an elliptic curve and a cyclic subgroup over n. Elliptic curve over C. And this is a subgroup of order n, finality n. So we write two such pairs, we say they're equivalent if there exists an isomorphism phi. Remember, we classified such isomorphisms, basically multiplication by non-zero complex numbers from one to the other, taking C to C prime. Okay, we're going to look at isomorphism classes of enhanced elliptic curves, and a clever choice of notation, we'll drop the round brackets and replace them with square brackets to denote equivalence class. There should be technically another round bracket there, but it's dropped in the book. Let's follow that. Okay, so this is all isomorphism classes of enhanced elliptic curves. Okay, so this is a set S naught n. Similarly, one can make this definition twice more. So enhanced elliptic curve for gamma 1 n is a pair consisting of an elliptic curve, and this time he writes Q. This is an elliptic curve with a complex number, just a complex torus. Not writing over C each time. The subgroup of, sorry, a point of order n. The point of order n in the elliptic curve. And again, we say two pairs are isomorphic if two such pairs are isomorphic if there's an isomorphism. I want you can give it a name, E to E prime, taking Q to Q prime. And then this notation S1n, let S1n be the set of equivalence classes. Finally, similar definition for gamma then. Is a pair, an elliptic curve, and this time a pair, the second coordinate itself a pair. So 2 points, PQ. I realize I'll need the way pairing, which I forgot to define. Okay, I'll do that now. Such that P and Q generate the n torsion. This notation here means all elements on the elliptic curve killed by n times x equals 0. X is a point on the curve. By the way, what's the size of this group for people who are just starting off? Elliptic curve is C modulo lambda, right? So what are the n torsion points there? They're basically, take anything at lambda with the denominator n, right? 1 over n times lambda, and modulo lambda. And that group is isomorphic to z mod n squared, right? Z mod n times z mod n. Okay, so so we need P and Q to be a basis of that space, and more than just a basis, we also require the wave pairing. I think it's called En or something fancy like that in books, but let me just be naive and call it diamond bracket. This is wave pairing. So this is a fixed primitive capital Nth root of unity, and it's that one. Okay, so what is this wave pairing? So it's a pairing from the n torsion to the n torsion, cross n torsion to nth roots of unity, and it's given by the following formula. Where did I have it here? The definition within the definition. Sorry, I should have done this earlier. So suppose E is C modulo lambda, then the wave pairing diamond bracket from En cross En to nth roots of unity, which I'll denote by mu capital N. So following nth root of unity, pairing. So if you take 2 points of order n, it's a particular nth root of unity. What do? Take some matrix, determinant of this matrix, where, so if P and Q are n torsion points, you can always write them by change of basis by an element. Let me just call it gamma. Gamma is a 2 by 2 matrix. Times more or less the canonical points. The first one you take is omega 1 over n. Second one is omega 2 over n. Right? These are also n torsion points. Right? We add these n times, then they're n torsion points. Any two n torsion points by write as a linear combination, A omega 1 plus B omega 2, and Q can be written as C omega 1 plus D omega 2. Then gamma be that matrix. Gamma may not be invertible, right? So because P and Q may not be a new basis. So this is just an element of M2 Z mod N. Right? So wave pairing is defined a bit more generally for any 2 points, n torsion points. So this determinant might be 0 or something. N. But anyway, the interesting case is when it's invertible, and it's this. I'll try and tell you where this shows up when I'm done with some of the proofs. Exactly. Okay, so anyway, so we have 3 different moduli problems: elliptic curves and a subgroup of order n, elliptic curves and a point of order n, and then elliptic curve and 2 points of order n. Did I write that? Yeah, PQ generate En, in particular, they're points of order n. And the wave pairing of them is a particular fixed nth root of unity. Okay, so that was a long definition. Let me try and write the theorem over here. Sorry? Oh yeah, I forgot S of n. Yes, thanks. So good, I have some space here. So similarly, right? I didn't define it, I didn't define the equivalence relation also. Let's sidetrack by the wave pairing. So EQ, the obvious definition, is said to be equivalent to E prime P prime Q prime, if there exists an iso, E to E prime, taking P to P prime and Q to Q prime. And finally, we define S of gamma n be the set of all such equivalence classes. Okay, so here is the theorem, last theorem of this lecture, and we'll try and prove one thing at least. So I'll try and prove one of the parts of this theorem. So the first statement is that the representatives of these equivalence classes can be taken to be familiar things, or S naught n, they can be taken to be E tau fine. I was not supposed to write up here. Okay, where should I write this E tau? So E tau is just C modulo lambda tau. It's just convenient shorthand instead of writing C mod lambda tau every time. E tau is just C modulo lattice span by tau and 1. So this is abstractly just some E comma Q, E comma C, but you can always replace it up to isomorphism with E tau and this particular subgroup. Okay. Similarly, S1n can be, let me just look at the point. And finally, there's always a representative in S gamma n. Is it called Sn or S gamma n? Maybe it's called Sn. I wrote S gamma n there. Maybe it's better to, yeah, Sn, let me write this as Sn. I don't know what's there in Diamond Sherman, but probably Sn. Okay, just to the notation consistent. So S of n is given by, again, E tau, and now two canonical points, tau over n plus lambda tau, in this order, 1 over n plus lambda tau. You can always find a representative of a particular kind. Okay, that's the first part of this theorem. Moreover, I'm going to write all of these, plan it better than how it's written in my notes. So moreover, 1, they're all appearing on the same line. 1 always appears on the same line. Two such things are isomorphic in the first case. If and only if tau is equal to tau prime in the quotient. So let's write that as gamma naught n tau. This is the orbit. I follow this slightly pedantic notation in dimension. Modulo gamma naught n, tau is equal to tau prime. Okay. Similarly, two more statements. E tau. You can see the second case has the least notation, and that's the one that will prove. This is equivalent to E tau prime, 1 over n plus lambda tau prime, if and only if gamma 1 n tau equals gamma 1 n tau prime. Finally, 3. E tau, now we have a pair, tau over n plus lambda tau, 1 over n plus lambda tau is equivalent to E tau prime, 1 over tau prime over n plus lambda tau prime, 1 over n plus lambda tau prime. I got all the brackets there. And all the primes, hopefully. If and only if gamma n of tau is equal to gamma n of tau prime. So tau is equal to tau prime in H modulo gamma n. Okay, so maybe the final conclusion of this whole thing, putting the respective ones together, and similarly 2s and 3s. 1 respectively 2 and 3 together. We conclude, trying to erase these modular curves, they're just here. They're going to come up in the theorem now, but thus, this is all part of the statement of the theorem. In case 1, you have a bijection between S naught n and Y naught n. Y naught n was H modulo gamma naught n. I just erased it. Similarly, S1 n. Thus, there exist bijections. I hope you can read this. Y1 n, and finally, right? 1 and 2 imply 3, because you can always change your representative so that it's got some upper half plane things in it. Instead of an EC, you can write it in this format which has a tau in it, something in the upper half plane, right? The upper half plane appears, and then what are the ambiguities? They're given exactly by the second part. Might be some typos, yeah, where? First line, second part here. Ah, yes, and the top right, thanks. Okay, so let's do a proof of this. So I'll prove part 2 because it has the least amount of notation, but maybe some comments on the other parts. This wave pairing condition, I was thinking a little bit about it forthcoming. Just doing it at TI4. It shows up in the surjectivity of the map from S gamma n to, sorry, S of n to H mod gamma n or Y of n. So anyway, you have to figure out where exactly you need that condition with the wave pairing. All right, but let's prove 2. Okay, so if you've seen this before, again, it's slightly irritating, but if you haven't seen it, then it's really remarkable stuff, how everything works out so nicely. Okay, so let's do the surjectivity first. So these are bijections. So when I say surjectivity, I mean for these maps. So surjectivity. So start with an abstract pair. We're doing case 2. So we're taking a curve in a point of order n. Okay, then we're getting the enhancement, just as an elliptic curve, a complex torus, we always know it's of the form C modulo lambda tau, right? So the first coordinate is not an issue. but you have to massage a little bit. So in fact, that tau is not a good thing. Let's call it tau prime. We already know that E is isomorphic to C modulo lambda tau prime, let's call it, for some tau prime. Right, this is because of complex tori up to iso is in bijection with H mod SL2Z, something we said right at the beginning. Right, every complex torus can be written as a isomorphism as a E tau, or E tau prime in this case. Okay, so I'm using that fact here implicitly. Just write this elliptic curve as a complex torus, but choose, let's call this tau prime, the lattice. So write Q, the point of order n. So every point of order n looks like C tau prime plus we just discussed this orally. Right, it's 1 over n tau modulo tau. So it's C tau prime plus D over n plus lambda tau prime. And I made a small mistake here. I should have said, okay, it's gone now. But when I said point of order n, I should have said exact order n. I think I just erased everything. Whenever I said order n for points, I should have said exact order n. I'm going to need that now. For subgroups, it doesn't matter. It's just order n, so there's no exact order. The size is just n, but order of a point shouldn't be dividing n. They should be exactly of order n. So typo there. All that has to be changed. So because of this condition that is exactly of order n, we can even assume that C, D, which are integers, and n, GCD, the greatest common divisor of these guys, is all 1. Otherwise, you can divide, right, by a common factor, and we have smaller order. Okay. So somehow we want to get rid of that CD. That's why we wrote the tau prime. We need to do some tricks. All right. So because these are co-prime, therefore there exists an A, B, K. Right. This suggestively as AD minus BC minus KN or plus KN minus KN maybe is equal to 1. Some integers A, B, C, A, B, A, D, sorry, A, B, and K. This is A, B, and K, and Z. Right, so this exact order n condition is really important. All right, so how does one use this relation? So under the map from M to Z to M to Z mod n, we see that the matrix ABCD winds up in SL2Z mod n. Right? It actually maps to SL2Z mod n. Right? Because the determinant was 1 modulo n. Okay, now there's another fact I'm going to use from group theory, that the map from SL2Z to SL2Z mod n is surjective. So we can actually assume that this matrix ABCD belongs to SL2Z. Why is this? Because any other lift will just change C and D by some nth thing, right? Multiple of n. And that doesn't change Q. We change C and D by adding on n's, then that doesn't change Q. You may always assume that your matrix is actually in SL2Z. That's a little trick. All right. This map is surjective actually. So up to replacing this by some other lift, then take that C and D there. Doesn't change anything. C prime, D prime will give you the same Q. All right, so what does that help? How does that help us? So now, notation, let tau. So now we finally have tau. We want to get a tau into the picture. The massage thing so that tau shows up. I mean, so that in the tau format rather than the tau prime format. So let tau be this, let alpha be the denominator. That's a complex number, non-zero. Right? Non-zero complex numbers are good. Multiply tori by them, get different tori. These conditions say that alpha tau is equal to, if you multiply these two numbers, you get A tau prime plus B. And use these formulas again and again. So write them explicitly. What do we notice? So do some computations. Then if you multiply alpha by lambda tau, what happens? You get Z alpha tau plus Z alpha, right? Lambda tau is spanned by tau and 1, which is Z. Alpha tau is the numerator, I think. Yes, A tau prime plus B plus Z, and tau alpha was the denominator. C tau prime plus D. Right? But we had assumed ABCD was in SL2Z, right? So by that lemma at the beginning of the lecture, this is just Z tau prime plus Z. The other sort of direction of the lemma, more easier direction maybe. Anyway, that lemma was an if and only if condition. Says if you change the basis by an SL2Z thing, you get the same lattice. And this is exactly lambda tau prime. Right? So this string of equalities shows that multiplication by alpha takes the lattice lambda tau to lambda tau prime. Okay, a similar computation. For the point of order n, okay, so this one is easier. C tau prime plus D over n plus lambda tau prime. Right, because alpha takes lambda tau to lambda tau prime, so I write plus lambda tau prime there. And this was exactly the point Q, which we started with. Right, so this messy point Q now became much simpler. If you multiply by alpha inverse, then that point Q is nothing but the point 1 over n plus lambda tau. So summarizing. Let me write maybe one line here. EQ, my multiplication by alpha right? Alpha takes E tau to E tau prime, and this point 1 over n goes to that C tau prime plus D over n. So these are isomorphic, and therefore their square brackets are the same. So we've done part 2, part 1. First part of part 2. You can always write your representative in this form. Right? The rest of the arguments are very similar. I think I started at 11, but I think I only have 2 minutes. So it continues in this vein. So let me just write what you have to check maybe rather than checking all these things. So is it well defined? So we get a map now. So moral of the story so far, at least we have a map from S1n surjectively onto Y1n. Right? Given any, sorry, maybe the other way around. From the upper half plane to S1n. Projection. Given any EQ, you can always write it using taus. Okay, so now one has to do some various other things. One has to check that it factors through gamma 1n. The check exactly very similar computation, but I've run out of time. So this factors through H mod gamma 1n. In other words, the tau that you started with, if you replace it by a matrix gamma tau, or gamma is in gamma 1n, then you'll wind up getting the same elliptic. Very similar computation. And the third part is also very similar. And in fact, once you do this, is exactly a bijection. Okay, so this more or less gives a sketch of the proof of part 2, and the other parts are very similar. So you might wonder where the one final remark is, you might wonder where the wave pairing shows up in part 3. I think it's used in the surjectivity of the map. The well-definedness and the injectivity of the map are okay. You don't seem to be using the wave pairing anywhere. But if you try and prove the surjectivity, you'll need this wave pairing thing. Okay, so any quick questions?